Hi everyone, I'm James. I'm representing San Jose State University today on behalf of my research partner Surabhi Gupta and our project advisor Dr. Magnolini Aranaki. More specifically, deep learning and AI medical imaging for stroke diagnosis is also my master's thesis research. So I'll be sharing a progress update on how things are going.
Perfect, thank you.
Here are the different topics that I'll be covering today. So why AI is essential for stroke diagnosis? Stroke is the second leading cause of death, making up 10% of all cases worldwide right after heart disease. And when we think of stroke, we're typically working with radiologists to diagnose for two different types of stroke, ischemic or hemorrhagic. And most likely you've probably met someone who may have been paralyzed on part of their body or speech impairments. These are often side effects of stroke. In the case of ischemic stroke, typically something to watch out for is if you have high cholesterol, those can form into blood clots that get stuck in the blood vessels within the brain, causing lack of blood flow to other areas of the brain. Similarly with hemorrhagic stroke, these are where aneurysms can form. So these are like little cherries that form in the blood vessels and then they burst open, and in this case, blood seeps into the brain. And this is actually more tragic than ischemic, so something we typically want to watch out for. Now, another issue that comes up with stroke with radiologists is the massive amounts of data that's being accumulated. So typically, radiologists are working with CT and MRI 3D scans, and so you can imagine a radiologist who's visually, textually annotating for stroke. There's not enough of them who are able to work with this massive accumulating amount of data. So this is where we can tie in AI stroke diagnosis systems to be able to learn from the radiologists and then meet this exponential growing demand of big data that we can then also prevent human exhaustion, human kind of errors that could come up with diagnosing stroke. So more specifically, getting into some AI areas of how we can help with stroke diagnosis, we can utilize deep learning computer vision, where we utilize these convolutional layers that can work with lesions of varying sizes in the brain, learn from 2D and 3D types of data, and then perform well in clinical applications such as lesion segmentation, where we're typically tracing for either these large areas of stroke for hemorrhagic because of the blood leakage, or smaller areas of stroke where we're looking for very small targets of interest. Again, deep learning is very powerful because we can utilize it to learn from the different medical imaging technologies. A human would have to learn how to identify stroke lesions from these different medical imaging, whereas AI can learn really quickly. Another area that's very helpful is in NLP with image captioning. So oftentimes what happens with MRI scans is there's a radiologist who's doing a clinical assessment, a write-up on that MRI data. And so we can generalize clinical notes for them, and we can take it a step further for even more time-saving tasks, where we can do report generation, sentences, paragraphs. We can generate templates for the radiologists and save them a ton of time. So our methodology that we're looking at is this AI stroke diagnosis system, where we're working with different types of stroke data. One is publicly available called Atlas 2.0. It's really good for computer vision, but it lacks in the text annotations and NLP. So we recently got access to a private data set for ICPSR, known as ICPSR 38464. And the one that stands out here is the NLP side, as well as computer vision side. The issue though was the ethics of AI. So we had to go through some agreements with ICPSR data repository, going with our institutional review board from San Jose State, to say we're not going to make this data set publicly available so we don't compromise patient confidentiality. And then I'll dive into the other areas of stroke diagnosis system data analytics, stroke lesion segmentation, and lesion image captioning briefly. So we've had access to the stroke data set Atlas 2.0 for a while, so we've made some great progress there on the computer vision side, but we haven't yet worked with ICPSR enough yet. So we actually, from the NLP side, work more from natural image captioning, which I'll dive into soon. So here's just a brief comparison between the two different data sets. And then our data analytics portion focused a lot on what kind of insight we can gather from the stroke data for Atlas 2.0. Primarily, we were looking at, can we utilize it for NLP processing? We already knew we could do it for computer vision. And so here's just some of the data that we found. About 60% of subjects have single lesion, whereas 40% have multiple lesions. And then the primary, secondary stroke locations, I'll show a graph in a moment for the top 10. Days post-stroke, 1 to over 10,000. And then only 10 patients been checked more than once. So I'll dive into some of the difficulties that we faced. Here's a set of graphs for the primary and secondary stroke locations, and then the findings. So the main thing with this was, typically when we're doing image captioning, we're looking at an image and then a set of samples that are different image captions that can map over to an image to generate those captions. Atlas didn't have that, but ICPSR from their publication reports that they do, as well as report generation. Stroke lesion segmentation. So this is actually very challenging. We can't just jump straight to tracing out these small lesions within the 3D MRIs because, well, in this case, I'm talking about UNET. It's one of the popular deep learning models in medical image segmentation, the medical imaging field. And if we were to jump straight to UNET, it would also require a lot of time being spent toward training the deep learning model. So we actually do another pre-processing step called skull stripping segmentation, or you could think of it as brain tissue extraction. So with this, we use 2D UNET. You can see here these bars that go small, and that's known as an encoder, and they're extracting out image features. And then you see these bars that are increasing here, and that's a decoder. So the model's taking the image features that it learned from to reconstruct a new image with the target of interest from those image features. So in this case, you'll see pretty soon, brain tissue extraction, the model learns how to draw out just the brain tissue. Later, you'll see stroke lesion segmentation, where it's focusing on particular stroke lesions, which the example will be ischemic stroke in a bit. So skull stripping segmentation, with Atlas 2.0, unlike ICPSR, it did not have the labels for doing skull stripping segmentation, so we had to go with an alternative data set, NFBS data set, train our model on that. Then you can see the qualitative results are pretty good, and then we tested it on Atlas 2.0. So this would be that pre-processing step that we perform. And you can see the target of interest is relatively large. Our metrics are pretty good as well. And then in this case, we get into stroke lesion segmentation. So initially we tried 2D UNET, and we took all the 3D MRI scans, we converted them over to 2D, we trained a lesion segmentation model on that, and then we adjusted the different batch sizes per 3D MRI scan for the stroke patient case. And we found that when we had small batch sizes per 3D MRI scan for the stroke patient, it didn't perform so well when it came to loss and IOU score. When we started increasing the batch size, so that you can think of that as, here's a patient's MRI scan of their whole brain, that's 3-dimensional, it actually started improving. So not this particular chart, but we have new data that's coming out where the loss is actually a lot smaller and the IOU score is getting higher. And the goal here is to try to trace out small lesions. So the future goal here is to get towards stroke lesion image captioning, which we can do with ICPSR data set. We just got access to it, downloaded it. This is one of the state-of-the-art architectures out there called CapCam. So they're able to take x-rays and these image captions, create a word embedding matrix that does the image captions map to image IDs to map back to these image features here of the x-ray. They go through this generator. Main thing you can think of is it's just generating image captions, maps between the image and the captions. And then we have a discriminator and evaluator. This is also getting to a reinforcement learning kind of process through trial and error, where based on how well the model performs, it gets very high rewards, and we can then reinforce the generator to improve better. So there's still some improvements we can make here. The data shows we can make some improvements there. Our natural image captioning architecture still has room to improve because we have to adapt it for stroke lesion segmentation. Here are just some of the brief results. And then our anticipated results is we have benchmark CV and NLP models that we can deploy to, say, H2O Wave or 3D Slicer. And we're hoping that we can assist radiologists in diagnosing the growing number of stroke patient cases and hopefully be able to detect it before the human eye can see it, like AI breast cancer diagnosis. Thank you.
Wonderful, thank you. We have a few minutes for questions, but we do have two judges that if we could allow them to ask their questions, then we'll open it up if time allows. Judges?
Two-part question. First, thanks for describing how some of the data sets were insufficient and you had to train models on other data sets to make up for deficiencies in the first data set. So to build on that, what other, how many of these deficiencies in the data set did you discover? Were you aware of the limitations of these data sets going into the project?
So I did read on their publications Atlas 2.0 versus ICPSR 38464, and from my understanding from their publication, their text annotations were supposed to be like one-on-one point with ICPSR, which when we actually further analyzed their text annotations, it turned out not to be the case. So we looked at some other examples like the Flickr 8K data set for natural image captioning, and then the OpenEye chest X-ray data set for medical image captioning, and found that whole difference with multiple image captions per image. And so we decided we can't do NLP yet with Atlas, and that was one of the big hindrances on the the image captioning side.
And the second part of the question, with ICPSR 3864, there's I think like 3,000 or 4,000 data points. Would your research suggest that that is enough data points for to get an accurate model?
I believe so. From the different publications I've read so far, and Johns Hopkins cited a lot of publications in their deep learning ischemic stroke lesion segmentation. They not only account for the ischemic stroke, you saw like small lesions in this presentation, they also account for the hemorrhagic stroke. And one of the other things with their data set is they make a classification between ischemic and hemorrhagic, whereas Atlas 2.0 doesn't do that. So we're able to say with Atlas, non-lesion, lesion classification, draw the lesion, but we don't know which particular type it is. So to benchmark with some of the other state-of-the-art methods, it would be very helpful to account for ischemic and hemorrhagic. In fact, we were in communication with one of the faculty members from Johns Hopkins who said they were making great progress on ischemic stroke lesion segmentation, but there's still room to grow in hemorrhagic. So they were recommending to us to do an area of transfer learning toward that. But yeah, we think it'll be very helpful to make further progress with ICPSR, and we're looking to do that next semester.
Yeah. First of all, congratulations, that was a nice presentation.
Thank you.
Very great topic.
Yeah,
Yeah,
definitely.
I have just some quick questions like from a classification point of view, you have this 3D scans and 2D scans, right?
Yes.
Yeah, so like actually it's in line with what I had to ask, like how much do you think the data you have is sufficient? Do you need more of those 3D scans or the 2D scans or the lesions? Or what do you think is lacking in what you have in data sets?
I think it's definitely the three-dimensional data, and then not only to account for tracing lesions and tracing out the brain tissue, but giving some understanding to what's exactly going on with the computer vision side. Oftentimes in medical imaging in general, they focus a lot on the computer vision side, but not enough on natural language processing. So we are building up the computer vision side, but we're also trying to be one of the first teams from SJSU as well as some other schools to show the benefit that NLP can bring to medical imaging. And there's actually a professor from University of Waterloo named Dr. Tehush, who's been definitely recommending more students, research teams getting involved with NLP side of medical imaging.
Judges, any other questions? Any other questions from the audience? We have about 30 seconds. Sure. Thank you.
Yeah.
Hi James, Deborah, I'm a nursing professor. So
Great.
I have just a very different question. The timeliness of the imaging. So when a stroke patient enters the emergency room, the first thing that we have to know is it hemorrhagic or ischemic. because if we give a blood thinner to a hemorrhagic stroke patient, we'll kill them. How quickly can this happen when AI comes in and looks at this? Because we need to do it within, a few minutes. Have you thought of that?
Yeah.
The quickness of it?
I have, and I've done a little bit of research into CT versus MRI scanning
Yeah.
and how MRI can show us within 30 minutes or faster,
Right.
that kind of information, but then it really, I think, falls down to the access to the clinical assessment we have for those MRIs. So if we have access to that, then the MRI, this is all based on the radiologist's assessment, so
Right.
the model learns from them, and so I think ethically, because it's based on radiologists' understanding of their findings, we could trust in the data, since it's based on radiologists' assessment, a lot of them.
I do apologize, I don't mean to, because it's great when there's a conversation taking place.
Yeah.
Interest, you guys can continue
I will.
afterwards. Yeah, we want to be sensitive to everyone's time constraints, so thank you so much, James, that was wonderful.
Great
And
job.
just a short 5-minute break,
Thank
if you
you.
guys want to run
Thank
to
you
the
for the
restroom,
questions.
and then we'll get started. Thank you.
I have 1,000 questions.
I definitely put a lot of time into the science side, not
Yeah.
only the AI piece. Yeah, I feel like it was really important.
Yeah.
So Ricardo, I apologize, is Ricardo here? Ricardo's our next